So let's continue our discussion of Newton's laws with Newton's laws 2, the revengeing. I realize revengeing is not a word. Please do not email me telling me that I have made a spelling error. It's there for humour. I did consider briefly calling this Super Newton Boss Fight Go, but felt that might have gotten a little too manga. So, in terms of friction, last time we introduced the concept of friction and we didn't really do much with it. This is where we're going to discuss friction in much more detail. And by friction, what we're really talking about is a force that's introduced as two surfaces interface and an applied force is applied to one or both of those objects. So what we really mean is, say here, Indy being dragged along the ground, there's going to be a force of friction between him and this sand on this road. So in terms of friction, we discussed this previously, we have two types of friction. One is kinetic friction, Fk, and the other being static friction, Fs. The only difference between the two are these coefficients of friction. Mu k is a coefficient of kinetic friction, mu s is a coefficient of static friction. N, in both of these cases, is our normal force, the opposing force to the gravitational force, so usually positive mg, unless modifications are applied pulling our object upwards. What this means, for our purposes, is that Fk usually has a coefficient of friction, or for our purposes always has a coefficient of friction, which is lower than that of mu s. That means mu s tends to give an Fs which is a bit larger than Fk. This means that for a stationary case, an object that is not moving, the force of friction is usually higher than for an object that is moving. Static friction tends to be higher than kinetic friction. And we've seen this previously. And that gives way to a graph such as this, where this is frictional force here, and this is driving force here. Static friction is shown here. So here we have a static region and kinetic region. As we increase our driving force, force goes up and up and up and up. That means our static friction increases. Eventually, we reach a point where our driving force exceeds our static friction. That means the block is about to slip. As the block slips on its surface, you can see that the force of friction drops down, and this whole thing should be undulating just like this part of the graph is. As this drops down, this is showing that our force of kinetic friction is less than our force of static friction. That means it's easier to keep an object moving than it is to start an object moving in the first place. And that point where our driving force just passes our static frictional force is going to come back to us again and again, because it's a point where our driving force F equals Fs and allows us to do a lot of calculations that we wouldn't otherwise be able to do. But as we've seen previously, our main goal when we're dealing with F equals ma and calculating forces is to usually find what A is. And this often means engaging with our equations of motion that we've already seen again and again and again. So let's look at a situation that's very kinematic in detail. So here we have a hockey puck. The hockey puck is hit and given a velocity of vi equals 20 meters per second. The puck then slides 115 meters on the ice before stopping. The question is, what is the coefficient of friction between the puck and the ice? So this is a moving situation, so we'll have Fk. Fk is going to be equal to mu kn. The question is asking, what is mu k in this case between these two? And figuring out what a hockey puck is made of and looking at the coefficient of friction between it and ice may be a little difficult to do on the fly, so that's why we're calculating mu in this case. What are you given? Not a lot. Initially, it seems all you're given is the initial velocity the puck is moving with and a displacement s on the ice. There is a key point here that you should actually get from question interpretation by now. The hockey puck is hit and given a velocity vi of 20 meters per second. It slides an s of 115 on the ice before stopping. So the question is telling you explicitly that Vf is 0, even though it hasn't stated it in numbers. Make sure you're interpreting these questions correctly. You should be writing this out as Vi equals 20 meters per second, S is 115, Vf is 0 meters per second, and our coefficient mu k is question mark, what we want to find. So not a lot of information seemingly. And of course, as I've said, with everything we've ever done, draw a diagram. So here's, again, the same diagram we saw previously. I think I've put the arrows the opposite ways. It really doesn't matter as long as it's all there. N will be here, negative mg here, Fk, and F giving rise to our motion. Are we dealing with Fk or Fs? We've already said we're dealing with a case of kinetic friction. Fk is going to be constant in this situation and acting opposite to the direction of motion and constantly slowing this puck down, hence it reaches its velocity of 0 by the end. So this means we have a uniform negative acceleration from Fk. This means we could look at Newton's laws, F equals ma, and the distance. Attempting to use F equals ma here might be a little bit on the difficult side initially, as you've given no accelerations. So in terms of equations, as we always do, let's look at the forces in the x direction. Our forces in the x direction, from our diagram of course, will be negative Fk, Fk from the right to the left, and our motion, the force of our motion, ma, m of the puck, times its initial acceleration. So the forces in the x direction will be negative Fk, and we're saying they're equal to ma here, as the object does come to a stop. Our forces in the y direction should be relatively simple. No motion in the y direction in this scenario, but always make this statement anyway. Here we have mg downwards, giving a negative, and n upwards. Collecting these correctly, Fy now, or Fy net, or sum of Fy, will be n minus mg, which will give us 0, and a vertical acceleration of 0. Now, the formula you'll want to use, of course, somewhere and engage with, is Fk equals mu n. And one of the things to remember about this formula is Fk here is definitely in the x direction. But this force in the x direction has a heavy dependence on n. This is a force in the y direction. Now we're not mixing up our vectors here. We're not taking a motion in the y and applying it to a motion in the x. So we're not violating any of our previous rules here. But F is definitely dependent on forces in the y direction here. And that's something you really have to remember. So, from our previous definitions, n was equal to mg. If we substitute that here into equation 1 for the force in the x direction, what we'll have here is Fk, mu kn, will equal mu k mg. This is our normal force substituted in for n. So mu mg now is equal to ma. Now, you should notice from this particular equation that we now have mass on both sides of this. This is really useful and quite fortuitous that as m is on both sides of our equation, this will cancel, giving us a. So now we have mu and g, or essentially mu, in terms of the accelerations of the puck. So this is a negative acceleration. That means it's going to the left of our coordinate system. This is good. This means that this is essentially a force of kinetic friction. So mu k is constant, so our acceleration here is independent of the mass, and because it's a constant acceleration system now, we can take this a value and we can go back to our equations of motion. The equation of motion we're going to pick on is vi squared plus 2as here, and we're going to say that our final velocity, of course, is 0. So Vf squared equals Vi squared plus 2as. Here in the x, here's our initial velocity that we know we have. If we rearrange this, we can say Vi squared minus 2, now substituting in for a, so minus 2 mu gx now is equal to 0, because we know our final velocity is equal to nothing. So using v squared equals Vi squared plus 2as, we have described our system. So now we have the puck in terms of just its accelerations and its velocities. With this equation, we can now rearrange and find mu. Rearranging this equation, we'll get mu k is now Vi squared over 2gx. This whole thing now is in terms of acceleration and initial velocity. So mu k equals Vi squared over 2gs, substituting in 20 meters per second, 9.8 meters per second times 115 meters gives us a unitless value, of course, for mu k of 0.177. Now, when people attempt to solve this problem of the hockey puck, they usually see that this involves forces and immediately jump for an F equals ma solution. That's essentially what we did. We just had to get a little clever about how we defined our accelerations and how we found them. We also have a dependence of an x force on a y force here in terms of F equals mu n, Fs here, or Fk, or is always equal to mu n. So don't just try to immediately apply F equals ma in one direction and mu n in the other, and then force an acceleration out by using an equation of motion to slap into F equals ma. Here we found mu without actually engaging with the acceleration of the puck whatsoever in the x direction. So you can always go back to your kinematic equations and use them cleverly to solve out these situations. So let's take a look at another application, or several applications, of the force of friction. So here we're going to pick on this monkey. For some reason, this monkey has been presented with a box of bananas. The box weighs 40 newtons and rests on a horizontal surface. The coefficient of static friction now, mu s, between the box and the surface is 0.4, and the coefficient of kinetic friction is about half of that at 0.2. There are several questions here, A, B, C, and D. Well, first one talking about no horizontal force being applied, and then we're going to apply different forces to this box that we will deal with in turn. So the situation is, for your diagram, of course, you've got a weight of 40 newtons, you have an F of 6 newtons here, and of course you're going to have some static friction here that this monkey has to overcome after he's applied his driving force. You'll also have, of course, an N value opposite to this. So if this weighs 40 newtons, you know that your N is equal to mg, which is equal to 40 newtons. And of course, the monkey will push and push and push on this box until eventually he exceeds the force of static friction and his box will move. So part A. If no horizontal force is applied to the box and the box is at rest, how large is the frictional force exerted on the box? So right now the monkey's not too bothered about the box. Perhaps he's not hungry, perhaps he's looking in the other direction. But whatever his motivations, he's not applying a horizontal force. So what's the force of friction on the box if no applied force is given? So F, essentially, driving force, is 0. It's at this point where I have to really do the sort of countdown music and go da 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 da. Thought about it yet? So if there's no applied force in the horizontal axis, friction is a response force. It's a response force to any force that is applied to the system. So that means if there's no applied force in the horizontal axis, then there's no responding frictional force. So the answer here is Fs is equal to 0. Part B asks, what's the magnitude of the frictional force if a monkey applies a horizontal force of 6 newtons to the box, and the box is initially at rest? Well, our maximum static frictional force between the box and the surface is going to be Fs max. This is going to be equal to mu s, whatever our coefficient of static friction is, times n, the normal force. We know both of these from the initial question. Mu s is 0.4 and the applied force, the force due to gravity, the weight, is 40 newtons, meaning mg is equal to n, which is 40. This will give us an answer of 16 newtons. So the static frictional force that this box is responding with to the monkey's motion happens to be 16 newtons. He's only applying 6 newtons, so he's not going to be able to push this over here, as he's only applying his 6 newtons of force. Consequently, he has not made this box move. He's pushed with 6 newtons, and the box has responded with a 16 newton force, so the box will not move. That segues us into part C. What minimum horizontal force must the monkey apply to start the box in motion? Well, the answer just comes straight from part B. He needs to apply just over 16 newtons to get this box to move from the left to the right. Now this differs a little from part D. Part D now asks, what minimum horizontal force must the monkey apply to keep the box moving at a constant velocity once it has started to move? Now there's a key point here that often causes confusion that people miss. The question specifically states, what minimum force must the monkey apply to move at constant velocity? V is constant. If the velocity is constant, that means our accelerations are cancelling. And that is very significant to how we approach this question. So to move at constant velocity, the net forces on the box have to equal 0. And remember, that does not mean that the box necessarily is standing still if net force is equal to 0. If net force is equal to 0 by F equals ma, acceleration is equal to 0. So velocity is constant. So what the monkey needs to do is balance the force of static friction by applying a force of equal magnitude opposite to the direction of Fs. And what this really means is, at what point does the applied force equal Fk? Well, the applied force is going to be equal to Fk, which is going to be equal to 0.2 times 40 newtons. This will equal 8 newtons. Here, this is mu k now times n. So mu k was 0.2 and our n is 40. This will give us 8 newtons. So those are two situations of looking at how we can treat forces, driving forces versus frictional forces. And it's very important to remember the couple of occasions where you can really calculate out your forces. One of them being the point at which the block slips. What force of friction do you need to overcome with a driving force to move your object? The other being, if an object is moving with constant velocity, your accelerations are going to cancel. So let's take a look at another situation here. This is example heavy because we've already discussed how friction really works. So here we have a 2.5 kilogram block that's initially at rest on a horizontal surface. A force is applied horizontally of magnitude 6 newtons, but here a vertical force of P is also applied to the box. So there's two forces acting here, one driving force in the x direction and another which is pulling upwards on this block. The coefficients of friction for the block and the surface are 0.4 for static and 0.25 for the kinetic case. The questions here They're saying determine the magnitude of the frictional force if the force acting on the block is a magnitude 8, 10 and 12. So what we're saying here is we're modifying now the force in the y direction. So let's apply Newton's second law here. So here we can actually reason out our equations as we always have. We have a driving force in going to the right, we have a frictional force going to the left. Static or kinetic, this will always be the same. And we'll have F minus F is equal to ma of the block. You should be seeing now how this is always the equation that we actually contend with when looking at these situations. In the y direction now, we have our typical equation. N or Fn are interchangeable, but the force, the normal force, minus mg is usually equal to 0. But now we have P. We have this extra force added upwards. So we have to say P plus Fn, total in the upwards direction, minus mg is equal to 0. P plus Fn minus mg is nothing. Here, our force is 6 newtons for F, and m is 2.5 kilograms. So, part A, what happens now if P is equal to 8 newtons? Well, this will modify the expression for our normal force. So our normal force will be mg, our 2.5 times 9.8, minus, now, very important, minus what's being pulled up here. So this is modifying our overall force. So 2.5 times 9.8 minus 8 gives us 16.5 newtons. So effectively what we're doing is lightening this thing. We're pulling up on this and we're reducing the normal force, which of course affects our force of friction. That means if we calculate our friction, Fs will be equal to mu times n, which will equal mu s times 16.5 and give us 6.6. This is larger than the 6 Newton rightward force. So our applied force here was 6 newtons. We're getting back a frictional force of 6.6. So the block is not moving. If we substitute A into our above equation, then Fs is equal to P, which is equal to 6 newtons. Now what happens if P is equal to 10 newtons? Well, again, our normal force now will be 2.5 times 9.8 minus 10. This will give us an overall 14.5 newtons now. Let's recalculate our frictional force. So Fs will be mu n, and this will give us 5.8 newtons. Remember, our driving force here was 6 newtons. This means that our driving force, now we've pulled up on the block with 10 newtons, exceeds our frictional force of 5.8. That means the block is going to move rightward. The block moves, so we're dealing with Fk here. So Fk equals mu n, which equals 3.6 newtons. So what we would have to do is, as we have exceeded static friction, the kinetic friction on this system would end up now being the kinetic case. So we would have to use mu k in the kinetic times n. Now P is equal to 12 newtons. So in this case, Fn is equal to 12.5. So this is far less than the 6 Newton rightward force now. So if we actually look at the kinetic frictional force, Fk will be mu n, which will be 3.1 newtons. So our normal force is 12.5 here. So this is going to be mu times 12.5 and give us 3.1. I think it's worth looking through this and figuring correctly how you can work through these problems. Please substitute it in each time and convince yourself about what's going on in terms of the frictional force and how it's modified with n. So let's return to the case of the inclined plane that we've seen previously. Remember, in the case of the inclined plane, there are some very important things to remember, such as the component of the force acting down the slope here is actually mg sine theta, and not cos theta as it would be if the situation were sitting on a flat surface. It also changes our normal force, n, which gives us an mg cos theta for our normal force. So let's look at these effects and draw a free body diagram that shows both the XY orientation that we will use for this system and all of the components of the force on the block. In this case though, we're now armed with our concepts and equations for friction, and we're going to apply friction and make this a realistic problem. So when we place our block on the inclined plane, we have to think about where our XY axis is aligned. The other thing we have to think about are the forces at play. Gravity is acting down on this object, but because this object is on a slope, a component of gravity will act down the slope to move the object in this direction. Once we keep increasing theta, we'll eventually reach a steeper and steeper angle where the component of gravity down the slope exceeds the static frictional force that's holding this object steady, meaning this object will start to slide down the slope. As it does, friction will not go away. The regime of friction we're dealing with will move into the kinetic instead of the static, and that means there will constantly be an acceleration due to frictional force holding this block back and slowing it down as it slides down the slope. Now the point at which our force down the slope, which will be mg sine theta, exceeds our force of static friction is referred to as the critical angle, or theta c, the point at which the force down the slope is such that the block starts to move. So when we talk about our XY axis, remember we put our XY axis in this orientation. Thereby, X is going down this slope and we're only looking at a movement of the block in the X direction and not in X and Y, as we would if we put our axes in terms of the whole system. Now, remember we're looking for a point here where the force exceeds static friction. Here we have Fs for when the block is standing still, and once the block is moving, it'll be subject to Fk. But the direction of frictional force is still up the slope. This means there will be a force of friction, driving force due to gravity of mg sine theta down the slope. This has an angular component, of course, which means we can keep moving theta here until theta here equals theta c, a critical angle at which the block slips and moves from the Fs regime to Fk. We will have, of course, our normal force pointing upwards from the block against this surface. There will be a force due to gravity. Of course, it's going downwards, so this would imply from the vector that this is a negative mg cos theta, as this would be a negative mg sine theta. And we'll have mg, negative mg, and theta here, remember, is theta here. So theta c applies to both of these cases. So, here's our system that we just defined. Let's find the critical angle theta c at which this block begins to slip down the slope. First of all, as usual, let's define our forces in the x direction down the slope. Fx here will be mg sine theta, which of course we can always equal ma. As per usual, as per we should have seen when we talked about such things as the hockey puck, we have m on both sides of this equation. Cancelling m gives us an expression for force in the x direction that's purely based on acceleration, g, a, and the angle at which the inclined plane is held. So, rearranging for this, the critical angle for every single case you're looking at will always be the inverse sine of a over g. Now that takes into account the angle. The other part of this problem would be saying, well, what is our frictional force? Well, with frictional force, we have a very specific point, and that's the angle theta c that the entire system is rotated through, is actually inclined to, before the force is exceeded. So with friction, mg sine theta c will equal Fs. The force down the slope equals the force of static friction right before the block slips and moves into Fk. If this equals Fs, it also equals mu n. Our n in this case, remember, is mg cos theta, theta c, because we're looking at the critical angle. So mg sine theta c is equal to mg cos theta c. And I hope you can see where we're going with this. So here are our previous definitions. Here's n, and here's essentially our frictional force with n included equal to the force down the slope of mg sine theta. And these are the critical angles. These are the same angle in both cases. If we want to find out what mu is here, which is our unknown value, then the coefficient of static friction will be mg sine theta c over mg cos theta c. You can see now we have a sine over cosine situation. We also have a case of mg over mg. This will reduce down to give us tan theta c is equal to mu s. Or we can say in terms of the critical angle that theta c is the inverse tan of our coefficient of static friction. This is a typical result, and this will always occur if we're trying to find theta c. We can always use the inverse tan of the coefficient of static friction. This will also work for mu k. So remember, when we dealt with our force calculations, we can deal with an inclined plane, we can deal with a flat surface. We've got friction introduced. We've talked about the specific condition where our driving force exceeds Fs, the force of static friction. And that gives us an important point. When the force that we're applying exceeds the force of static friction, that's when we want to know what force that is. When does the block slip? So let's look at a realistic problem that involves forces in a straight line on a flat surface and also involves friction. So I realize this is a ridiculous cartoon, but it's often been a mystery as to how the Egyptians moved very heavy blocks. And some of the blocks on the pyramids weigh about 2,500 kilograms. In this particular case, one person could not pull this block, but I didn't want to make this entire example so complicated with a whole team of people and camels and whatever pulling the block that we ended up with a mess of a slide. So I abbreviated it to one person who would obviously seriously damage his back pulling this block. But anyway, so this one lonely man here is applying a force here along this rope to this block. The sandstone block is pulled along the road using a rope at an angle of 40 degrees. So theta here is equal to 40. What is the force required to start the block moving? We have a mu s, of course, here for brick on sand of 0.4 that we're going to assume is working. So of course this is our situation where we're looking at our graph, and he's going to apply a force and apply a force and apply a force until we hit this point where the block starts to slip, where our driving force is equal to the force of static friction. And of course we can look at the trigonometric functions here and realize we're dealing with a nice right angled triangle in those terms. So there's a question. Let's figure out what force is required to start the block moving. So what were we presented with? We had a theta of 40 degrees and a mass of 2,500. Mu s was 0.4, and we can resolve our forces using our typical sine and cosine functions. Our force, of course, is deflected through an angle theta. This means that our force that he's pulling this block with at 40 degrees is going to have an Fx and an Fy component to it. The Fy component, of course, is going to modify the normal force, and that means we have to take into account what's going on with friction due to the normal force, as well as the force in the x direction. But it doesn't matter what we're looking for, our approach is always the same, and that means we resolve our forces vertically and then horizontally, or you could do it horizontally or vertically, but treat them as separate and then put them together. So here's our crude diagram once again. Here we're looking at the y direction. We'll have n upwards and negative mg, and here's our little man pulling his block. This means our forces in the y direction. Remember, all of our forces, both in the y and x directions, are equal to 0. The block is in a static state. The force of friction has not been exceeded by the driving force. This means that all the forces in the y direction and all the forces in the x direction are equal to 0, and that's very useful to us. So we can safely say that the forces in the y direction all equal 0. That force will be equal to n plus f sine theta, the y component that the man is pulling with, minus mg. The normal force, of course, here, this is a statement of our force, is going to be modified by pulling up on it. So n, if we rearrange for n here, because this is equal to 0, will give us mg minus f sine theta. So this is our new n value, and that's what you have to consider, is what's happening to n because we're pulling up by this force. And that's why we rearrange to put this in terms of n, because we are going to put this into friction, and if f equals to mu n, that's where we have to put that in. So both Fy and Fx, remember, are equal to 0. Static friction's not yet exceeded. So that was our y case. Let's look at the horizontal x direction. So in the x direction, once again, Fx is equal to 0. In the x direction, we've seen this exact situation before. The force he's applying will be F cos theta, but minus Fs, the frictional force acting opposite to the block. This means that our force of static friction is equal to F cos theta. And that block won't move until we hit some maximum value. That means the block will only move when our driving force, in this case our F cos theta, exceeds Fs. And this is the point where the block will slip, when F cos theta equals Fs. So we've now defined our horizontal and our vertical forces, our x and y directions. Let's put them together. And the thing that puts them together, remember, is we have this Fs acting in the x direction, which has a y dependency. So let's look at our force of static friction. So Fs will equal mu n, as always. This means mu essentially is the same times n, which is now, as we defined in the previous slide, mg minus f sine theta. We know that everything is coming to 0, so we can set both the x and y components, in this case, equal to each other. The system is stationary, the block's not going anywhere. That means we can do this right now. If the block was moving, it could be moving at some unknown speed, but we know it isn't. So both the x and y components are equal to 0, which means in this case they are equal in magnitude to one another, and we can do this. So f cos theta is equal to mu mg minus f sine theta here. So here we're setting our x component equal to mu mg, and we're going to subtract our y component here at which the block is being pulled up. We can factor out mu here and say f cos theta then is equal to mu minus times minus f sine theta plus mg now. Convince yourself of this step. So that means f cos theta plus mu f sine theta is going to be equal to mu mg. This gives us a bit of an issue because now we have F in two places of this equation. Factoring it out will give you an expression of F times cos theta plus mu sine theta is equal to mg. This is the expression of force that equals our frictional force. That will give us F is equal to mu mg over cos theta plus mu sine theta. And this is always the result when we're dealing with friction and pulling our object at some angle. So, to complete this question, here's our expression, F is mu mg over cos theta plus mu sine theta. We can substitute in everything we've got. 0.4 for mu, 2,500 for the mass, 9.8, and our angle of 40 degrees at which the system was being pulled at. That'll give us 9,800 over 1.02, essentially giving us 9,578.2 newtons, or about 9.6 kilonewtons. Now the important thing to remember here is we've done everything in terms of the force and re-expressed it in terms of our frictional force and included everything in one expression. The most common error here is people doing F equals ma, comparing that simply to mu mg and then trying to press on through. That would be a very difficult way to solve this problem, and as such this is the recommended methodology. So when we're talking about friction, we've talked about Fs and Fk, our static and kinetic frictional situations. There is one type of friction we haven't discussed, and I'm not really going to go into too much, and this is referred to as rolling friction. I don't consider this a true friction. This is not the interaction of two materials. If you see rolling friction, which I won't really ask you about, this is due to the deformation of the material itself. So if you think about pushing a car, if that car has particularly flexible and squashable tires, is squashable a word? It is now. Then compressible would be the word. Then you have to compress the tires before you can make the vehicle move. As such, if you push the vehicle, you'll have to put energy in, force in to compressing those tires before you can look at a movement of the vehicle. And this goes for any particular material. If you're looking at a very flexible road, you might have to deform the roadway before the object will move. And this, of course, is to do with the elastic properties of the materials themselves. If you actually see this rolling friction, then the rolling friction is equal to mu r times n, where this mu takes into account the compressibility or elasticity of the material itself. We won't get into the deformation that results in the energy loss, and will restrict ourselves to Fs and Fk where possible. Which brings us almost to the end of our discussion of friction. And that means we just want to mention one more point, and this is the effect of lubrication. When we're looking at friction between two surfaces, the reason we need oil in cars and we need to look at mechanical systems having some form of lubricant, be it something like oil or WD-40, which wasn't actually invented as a lubricant, was actually invented to repel water from mechanical systems, but still acts very much like a lubricant. Then we need to know how lubricants work. Now we know that friction results in a loss of mechanical energy. If you rub your hands together, you will wind up with your hands warming up. This is energy leaving this mechanical system and going away from motion and going into a thermal sense. Technically, thermal energy is a form of motion. It's just not the mechanical input being equal to the mechanical output. We can also look at this in terms of force, that you're losing some acceleration every time you rub your hands together. So friction results in the loss of energy and means we have to put more force to keep our system moving. A lubricant prevents contact between materials and reduces the rubbing of material. When you put oil into a car, essentially that oil is creating an incompressible layer between the piston cylinders and the pistons themselves. This means that they're not actually in contact and the metal itself is not rubbing together and wearing out. And that means when we're looking at lubricants, we're not changing the value of mu. What I mean by that is here we have, say, a steel block against a wooden surface. The value of mu s and mu k comes from the bonding in the steel block and the bonding in this wooden surface. We cannot change that. That would mean transmuting the material in some way and changing its molecular bonding. When we introduce a lubricant, the reason that oil is a better lubricant than water is it doesn't compress as much as water. So if we introduce oil to a surface and spray it all over that surface, it sits between the block and sits between the surface it's running on. So in the first case, we're looking at the full effect of friction. In the second case, this object will slip on this fluid and it will prevent contact between the wooden surface and the steel block. And that means those little undulations in each of the materials, in the steel versus the wood, are no longer catching one another as they do in the top case and are slipping over the oil that lies between them. So a nice incompressible fluid, for instance, makes an excellent lubricant. Please don't consider that mu has been changed in these cases. That is not what's happening. Essentially, you're running on a new surface which has a different frictional force and preventing the catching and allowing the materials to slip. To finish up our discussion on friction, we've really talked about all the mechanical systems we can, and we'll talk about gravity later on in the class. But when we talk about something like friction, there is of course such things as tidal friction, which helps generate geothermal energy here on the Earth. There's friction on the Earth's core due to the fact that the moon is pulling on it, and it even makes the Earth a slightly oblate and more sort of ovoid than it does a perfect sphere. And tidal friction is actually slowing the Earth's rotation down. The moon was actually closer to the Earth at one point in history, and well, many points in history, and of course with the Earth slowing down, we're looking at longer and longer day lengths. At its most extreme, when we're talking about friction, we can look at something like the case of a black hole or the center of a galaxy which contains many black holes. And in these cases, in this particular slide, we have a very dense black hole with another star as its companion. And you can see it's pulling material off of this star, and that material is going to orbit around the black hole and fall into the black hole. And as it does so, it gets backed up and essentially has a traffic jam of material. This traffic jam of material ends up with incredible amounts of friction generated within, and this actually generates more energy than the thermonuclear reactions in a star. So friction at its highest level is one of the most powerful forces in the entire universe. And here's a nice simulation of the accretion disk of a black hole. And as you can see, here's the very, very hot material emitting a lot of energy, more than the numerous suns, as the material is waiting to spiral in to the gravitational singularity.